In this video I'm going to study noise in crystals, quartz crystals. And this is the setup I'm using. It is an interferometer, this part here, and two direct conversion receivers here with local oscillator here. And the signal source for the interferometer is this one from vent cell, a low noise oscillator giving plus 12 dBm of power. I will show the schematic diagram later in this video. Here is the Linrod screen after several hours collecting average correlation spectra. The green dots, it is the average of 30,464 correlation spectra, while the yellow dots show the average of 1,000, the latest 1,000 correlation spectra, while the white track up here is the normal power spectrum, summed for the two channels. The noise of this point in a bandwidth that you can see here, it's about 6 Hertz, is like this, and I can evaluate the noise, and you see within the bandwidth it's minus 158 dB, but it is also here 165 dBc per Hertz, because Linrod, when set into dB.Hertz, will also compute the bandwidth of this filter, the equivalent noise bandwidth, so it can correct the observed powers here to dBc per Hertz. Now I could step to different frequencies and evaluate the power at different points, but that will take a lot of time, so I will just press G and then give a file name to save this screen. The correlation advantage is 14 dB. That's the separation between the green track and the white track within this selected bandwidth. So it means that the green trace is at minus 165 plus 14. Sorry, minus 14 means minus 180 dBc per Hertz, approximately. I can evaluate all the different frequencies by looking at the saved GIF file. To make evaluation easier at close range, I can expand the scale in the X direction by clicking here. And collection of data is very slow, so it takes a little time, but here we have it. And I can check the correlation advantage at nearby frequencies by clicking here. I had 14.2 and I move 10 Hertz like this. And then it says 14.3, so it's very similar. And I go a little bit here. And the response to my mouse click is very slow. The bandwidth of the main spectrum is 0.8 Hertz, approximately. And it takes a long time. Anyway, the correlation advantage here is 14.1. So it doesn't vary, as it shouldn't do, because the white trace is the average of 1000 spectra, and the green is the average of many more. So this will be good enough. Well, I can expand the spectrum once more because I'm interested in this slope here. I will just save this first. G, and I call it expand. Then I expand it once more. And save this also. Let's expand number 2. Here is where I will place the device under test. At this time there is no crystal inside, just a wire. So first I am looking at the properties of the setup itself, with no object to study. And first I'm running it at full power, 12 dBm, but now I change this by inserting 20 decibels of attenuation into the interferometer to look at where the noise floor now will come. It is immediately clear that the uncorrelated noise did not change much. Here is what I had before, 164.9 or 165.4. And here is at 20 dB lower power, and it differs by almost nothing. 0.3 dB in channel 1 and 0.1 dB in channel 2. And it could be random variations. I don't know. And you can see also on the waterfall that the white line is where I switched the power, and you can see the width of the signal is slightly smaller. This is the signal that comes through the interferometer, so it is suppressed, balanced to ideally 0, but of course there is some level of the carrier because balance is not perfect. I have to wait until more than several thousand averages have been collected before I can evaluate whether there is a change or not in the correlated noise in the two channels. And until I get a valid power spectrum, I have to wait until 1000 spectra have been collected. And there are 300 now, so I go and do something else for a couple of hours. Now, with nearly 11,000 averages, the correlation advantage is 14.6 dB, very close to what I saw at 20 dB higher power. The big difference is I don't see the close range flicker noise that was present before. It should be reduced by 20 dB, and it means that it goes into the flat noise floor. Maybe one could see a couple of tenths of a dB waiting another 24 hours or so, which I will not do. The channel levels are here, 165.7 and 165.1. And I don't remember exactly what I had before, but very similar. I had evaluated the noise the standard way, look at previous videos in the Nerd series and you will find out what formula I'm using. The result at 12 dBm local oscillator power is minus 179.5 dBc per hertz for the flat noise floor, and half a dB below that at minus 8 dBm. But I didn't recalibrate for the 20 dB weaker carrier, so this should read minus 160 instead. This is the expanded GIF file I saved from Linrod. I'm using this EarFanView software to evaluate where the pixels are. First, I can just make a rectangle like this, and the lower line, roughly here, is where I have the flat noise floor. So it's the lower line where I have the mouse. So it is in position Y301. Then I want the vertical scale. So I have to place the mice on one of the blue lines, like that, and then on one other. So I'm going 10 decibels vertically, and that is 127 pixels. Then I want the horizontal scale from 10.0 to 10.050, 50 Hertz up. That is 594 pixels. And the X coordinate, I place both lines on the same position. The mouse is a little bit too sensitive. That's here. Then the position is 625 for the carrier. So I am with one side on 10 megahertz, and now I am 24 pixels to the right, and I have moved the cursor to come on the green line, and then I can read the coordinate as 248 on the position plus 2 Hertz, and then I go for minus 2 Hertz. I have to find 24, and then vertically like that, and that is 248. So it's fairly symmetrical. So this is what I have. I have measured the pixels plus minus 2, 3, 4 and 5 Hertz and converted it to decibels, and then subtracted the flat noise floor minus 190 minus 179.5. I will plot these numbers. So here is what the curve looks like, and it's of course the same you have seen on the screen now on paper, and it's correctly given in dBc per hertz. So I extrapolate a little bit. At 1 hertz it is minus 172.5, and the flat floor starts at about 20 hertz, and then it goes all the way. But there are some peculiarities, spurs and things, but not very much as you have seen previously. And these are the 4 data points, and that's what I could do with the current software. And here is a block diagram of what I'm doing. The local oscillator, the interferometer with the device under test in it, and right now that device is just a straight wire, so there is no device, it's just the interferometer itself. that produces the curve that I've shown. Ideally, there shouldn't be any flicker noise at all. So this is an artifact of some kind. It should go straight out like that. And I don't know from where it comes, if it is the connectors I'm using or something else. There are a couple of resistors because I have attenuation to do the balancing. Anyway, the interferometer is followed by a hybrid that splits the signal into two, and then I have two receivers, and that allows me to do correlation because I have then a 4-channel A to D converter, a UADC4, and the PC to run Linrod in it. Here is what the interferometer looks like. It starts with a stepped attenuator because when looking at crystals it's important to see how the noise changes with the drive level of the crystal. Low pass filter 15 MHz. That's because I don't want too much of 20 MHz and higher into the system here. A hybrid, 90-degree hybrid, splits the signal into two arms. One arm contains a box with switchable cables. The longest is a quarter wave, and then the others are a factor 2 smaller in, I think, 6 steps or something like that. I have forgotten that. Then there is an analog phase adjust. It's a hybrid and a dual gang capacitor, and the second, much smaller dual gang capacitor for fine adjust. Then there is an analog amplitude adjust. It has several, 3 of them, variable capacitors with resistors in series. And the capacitors have a maximum capacitance of the smallest 11 pF, the next one 40 pF, and the biggest one 150 pF. And the resistors are adjusted to make the tuning range suitable. The biggest one has an inductor in series to not produce any phase shift in its maximum attenuation position. And here is a stepped attenuator in 1 dB steps. And I have verified it by having a 1 dB attenuator as the DUT, and that 1 dB was a long cable, so I know that one was not noisy. So this one attenuator is okay for flicker noise, at least in the 1 dB position. The other leg has a coupler, an iron-free coupler that couples at minus 23 dB on 10 MHz. It allows me to send a signal from a signal generator into this leg. And then there's the second identical coupler by which I can take out the signals coming through here. It means the signal that goes through the device under test and that comes from the signal source, the local oscillator, the Wenzel here, which is split into 2 equal parts. And it also picks up whatever I have sent into this leg with this signal generator. This is for calibration purposes. At the output I have a 30 dB attenuator and then a splitter. The reason for the attenuator is that the spectrum analyzer sends some signal backwards, and I want it not to enter into the receiver. There is a directional coupler, so most of it goes this way, but it's reflected and it comes and causes a disturbance if I remove this attenuator. And then I also have a Perseus for fine adjustment of the levels of the 2 signals of interest. And then here is the device under test, which in the first series of measurements you have already seen is just a short wire. But here I will put the crystals. And then the two legs are combined in a hybrid, and the output of the hybrid has a sum and a difference. The sum goes through a 20 dB attenuator into the oscilloscope for channel 1, which I use for triggering. And the difference, which is ideally almost zero, I mean the carrier should be balanced to zero, and what remains is whatever noise that is introduced in this leg or in that leg or in both of them, because what happens here and what happens here is uncorrelated, so they don't subtract in the hybrid. And then I have a -9 dB coupler to pick up what goes through here, and that is to look at it with the oscilloscope. Low pass again to remove 20 megahertz and higher, an amplifier and the band pass for 10 megahertz, and a stepped attenuator, because when I replace the device under test, the misbalance is very large and the oscilloscope doesn't show anything because it's completely saturated, and this amplifier might also be saturated. So I turn down this to do a course adjustment, means select the correct cables and do a course adjustment of these things. And then I can return to 0 for this attenuator and look at the oscilloscope channel 2 while fine tuning the balancing up here. And then what goes through this -9 dB coupler goes into a hybrid that splits the signal in two halves that are sent into the two different receivers, RX1 and RX2. Here is what the receivers look like. Both of them are identical. The only difference is that one of them has a frequency control input while the other one has not. The local oscillator, there is a coupler, 20 dB coupler, followed by a 20 dB attenuator going for the PLL system. This is to attenuate the leakage from the other oscillator into this oscillator, because if there is a small leakage between the oscillators, there will be some frequency pulling, which means that at very low frequencies there will be correlated noise. So it's important that the PLL unit isolates well, and this is a further isolation between the two channels. Then the LO signal is split in a hybrid and run to two mixers. And the mixers want 23 dBm, and I have 27 to start with. Then for the receive channel, the signal from the interferometer is amplified in a noiseless feedback amplifier with about 10 dB gain, having 5 J310 transistors in parallel. It's followed by a 3 dB attenuator in order to set the impedance to a reasonable level, because the PSA 45043 doesn't have a well-defined input impedance at such a low frequency as 10 MHz. It's designed for higher frequencies, so it has a very high return loss on the input. And then the signal goes to a hybrid where it is split, and it's also run to the mixers. And the mixers then produce the I and the Q signals, and there is an audio section which has a filter that filters out 10 MHz, or rather 20 MHz, which is a strong component, but it cuts at some maybe a couple of 100 kilohertz. And then there is gain, not much, but some gain. And then there is the I and Q routed then to the sound system of the computer, the UADC4. And here is the PLL. Two amplifiers with MGA LM3689. They provide isolation because channel 1 is amplified, it goes here and it couples and leaks out and goes this way. But this one attenuates well in the backwards direction. And then of course there is the attenuator that I just talked about on the RX schematics. The PLL amplifier, it's just an operational amplifier with some filters on the input to stop the 20 megahertz from the mixer, so it uses only the very low frequencies. And on the output of the amplifier there is a selectable resistor and a big capacitor to create a large time constant. And I can select the time constant from, well, I don't remember, but you can see it in an earlier video in this series, 2 or 3 videos back. The time constant goes up to, I think, 30 seconds or something like that. And it's necessary to set a large time constant in order to do measurements close to the carrier, because otherwise the PLL is going to lock the oscillators and transfer the modulation on one to modulation on the other. Here is the Perseus, and I click on the signal and we have it here on 10 megahertz. This is what is originally 12 dBm and it's split into 2, so this represents about 9 dBm. And I inject a signal from this signal generator. It's 100 hertz up. And it comes here. So the signal from the local oscillator is here, and it shows about 0. And I calibrated it a couple of days ago and haven't touched anything since then. So things are pretty stable. Then I click on the injected signal, like that. And it comes here, and it should be at minus 50. Because that's where I have set it when I did the calibration a couple of days ago. And it shows minus 50.00. So this is perfectly okay. Then I go to the other window here, where I have the system with the interferometer. And here I have the signal at 100 hertz, about 10 megahertz. So I put that into the filter and look in the graph, and here you can see the level. And it shows minus 50, which means this scale is now properly calibrated. And I haven't touched anything, it's the same settings that I had while doing that measurement. I will now change some things. That's X and P for parameters. And I increase the bandwidth from asking for 1 to ask for 16 Hertz. So I get a bandwidth of 13 Hertz now. This will make things run much faster. And I have to move the window and things, so I switch off while doing that. The typical series resistance of these crystals on series resonance is 12 ohms or lower. They are rated 1 milliwatt drive level maximum, which means that the maximum current they could take is 9 milliamps. It means that in 50 ohms, 9 milliamps would give 4 milliwatts, and that's plus 6 dBm. Now, starting with 12, splitting into 2 arms, I have 9 in each arm, but the maximum I can use is 6. So I need to insert 3 dB of attenuation. That's here. 1, 2, 3. Now I have crystal number 163 rather than the wire straight between the B and C connectors. There is a tunable capacitor in series and a small capacitor here in parallel with the tunable. And I have tuned it for a 0 phase shift. I can see in the interferometer that the phase is the same as the phase as I had when this little white wire was across between the B and C connectors and with no crystal in here. And now it is well screened again. I have to redo calibration because I introduced 3 dB of attenuation, so when I read out here I read -3. So I have to change the calibration from 17.4 to -20.54, and then I read 0 for the carrier of interest, the signal from the vent cell. And then I check the reference signal here, and it's of course no longer at -50. Relative to the one that I have reduced, it's about 3 dB stronger. -47. So I have to change the injected signal by 3 dB or 2.7. And now the injected signal is again 50 decibels below the main carrier. And here I'm back in Linrod. The injected signal at 100 Hertz, about 10 megahertz. It's now at -53.7 because I reduced it by 3 dB and there is some loss because of the crystal. And 100 Hertz on the side, it means that it's attenuated by the same amount as the main signal, because the crystal in a 50 ohm circuit isn't very sharp in its resonance. So I have to calibrate this to show -50. So here we are. Now the system is calibrated again, and I can switch off this reference signal. And what I see now is pretty ugly. The crystal has all sorts of oscillations on the sides of the main signal because the power is too high. There are interesting patterns. This spur that comes from the crystal goes up and down in a funny way. Here I have run at different power levels. So this is with a 3 dB setting on the attenuator, the maximum power that the crystal should accept. And here is 3 dB more attenuation, and we can still see an elevated noise floor. So 6, 9, 12 dB. At this point there are some odd phenomena close to the carrier. And then 15 dB, 18 dB. Here it looks pure, but the carrier is 18 dB weaker. So to make an oscillator, this is not very good. So I will measure performance of, I will look at a couple of other crystals before deciding how to proceed. Here is another crystal, my number 161. It is more noisy and it has these ugly sidebands that travel up and down, as you can see. There is also, at an offset of 100 Hertz, a very narrow spur. This is because of my local magnetic fields. It's the overtone of 50 Hertz. To verify that, I have a signal generator here and I switch it on, and the frequency is 87 Hertz. And you can see I suddenly get new spurs. And at twice that frequency, but also at 87 Hertz, but twice the frequency is higher. And you can see it here. It's not quite stable, now it's 85 Hertz. So it should be 85 Hertz below, and that's here. This is another thing to worry about, the magnetic sensitivity of crystals. I guess the mechanism is that there is steel from the socket up to the crystal, and that steel is magnetic, and the fields will cause it to vibrate, and that will cause strain in the crystal, and that will affect the frequency. Or it will cause modulation at least. So I will look now how this crystal behaves when I lower the power on it. And here is what it looks like. The attenuator setting 3 dB, 6, 9, 12, 15 and 18. And the 50 Hertz spur, you don't see it in the spectrum, but we do see it in the signal evaluation. It seems to not drop immediately, but after a power reduction it goes down a little bit. But here it behaves differently. And I will look at it at even lower levels. So here is 18, 21, 24 dB. And the 100 Hertz modulation is still pretty strong. And I'm looking at it here. At 3 dB, the level was minus 127. And at 21, it is minus 148. The difference is 21 dB, and that's the difference in power into the crystal. So this is a linear phenomenon, which the noise is not. It seems, based on this, that I should study crystals with an attenuator setting of 18 dB and just look at a single frequency, maybe something like 25 Hertz, because that's in the flicker noise region here. So I will have to change the setup and do the calibration for that purpose. So these will be the parameters I use to go through several crystals to see how much they differ and to see how meaningful it will be to select them from this kind of measurement. So the offset is 25 Hertz, and this one, the properties is I have minus 145, well, minus 146 dBc per Hertz, and the correlation advantage is only 0.7 dB, so it's not much to take into account. So this is the interferometer, as I shown before, and the crystal is here at 15 dB below nominal power. So that's with a power dissipation of about minus 16 dBm in the crystal. Horrible. I have looked at 12 crystals at minus 18 dB and at minus 24 dB. And I found two that seem good, number 163 and 143. This one is very unstable, and it gives a lot of noise, also at minus 24 dB. And the other ones, there is one more that is unstable and one that is very noisy. Here, minus 122 or minus 132. So, lowering the power does not necessarily improve performance. Probably if I would lower power much below this, but then the crystal would be useless for oscillator building, which I'm intending to do with them. Before I started to build oscillators and filter and other things with these crystals, I measured their characteristics. And here are the ones I have now measured, sorted in descending order of noise, which means the maximum current I could send through the crystals before they started to misbehave. And here are all the crystals I had. The best ones start at 192, and they are mounted in some equipment, so I don't have them to study now. The best one here, number 163, is also the best one here. And then comes 147, which is unstable, and I did not detect that. And I don't see anything particular about it. The series resistance is 14 ohms, which is a little high, but not exceptional. I think resistances generally are a little bit higher than the average. But that's not the explanation. And how the frequency changes with the applied power, that's the resistance change here, it's not exceptional either. Maybe 143, but that turns out to be one that I found to be good. And the really bad one, number 199, it comes low in this list. It starts to misbehave in the previous study already at 10, I think, milliamp. Then that's a lot of current. Anyway, no definite conclusions. Here is a bad crystal running at minus 24 dB on the attenuator. And I just look at the waterfall, and you can see the correlation thing here. I clear it. And since things vary very rapidly, it isn't useful at all. Except maybe at distant, at large frequency separations. That's 200 Hertz out here. So you can see correlation is above power spectrum often, and sometimes the other way around, because things change very rapidly. I have now set the attenuator to 3 dB. Note that the strength of the sidebands is the same as before, or even a little better. It means that in dBc per hertz it is now 21 dB better. But at large separations we see some noise. So this is a bad crystal. Here is number 163, the best one, at minus 24 dB, means 24 dB attenuation. And I haven't changed the color scale on the waterfall. And I can look for the effect of correlation spectra by clearing it. And I have to wait some time until I see something. And only at very close range I see noise from the crystal. Otherwise it's the flat noise floor. And here is the good crystal, number 163, at 3 dB attenuator setting. And you can see the wide noise floor has gone up. And I think that's caused by the crystal. And we have now these phenomena. These are oscillations in the crystal. And they were present also, but less frequently, at the 21 dB lower power level. And of course the 50 Hz modulation comes up now. It wasn't visible here, maybe in the correlation. And I look at the correlation spectrum. But before that I have to readjust the interferometer balancing because the temperature is still rising slowly due to the heat generated by the power. And the correlation spectrum is not below the power spectrum at any place. It means that what I see is correlated between the channels. This peak here is the noise at DC for the sound card, so that is of no concern. And these lines is the 50 Hz going into the sound card. And this is when I adjusted the interferometer. Anyway, looking at crystals seems to be far more important than I has been aware of previously. The oscillations that we can see here, at higher resolution they look like this. So it is things coming up, and I don't know the mechanism of this.